Good afternoon, everyone. My name is XianfengHu. I'm very glad to be here and thank you for to the Beiforschke Foundation to be selected for this best PhD thesis. And my work is a collaboration between the Lulu University and Sverige methods. And the topic is mainly on the carbothermic reduction of chromite. First, I will just give some short introduction about chromium and chromium alloying in the steels. And the chromium is mainly from the chromite ore, and the extraction of chromium is carried out by the smelting reduction of the ore in the submerged arc furnace. And after the reduction, the melt is put out, and then cooled down and crushed, then be transported to the steel making plant. For alloy steels, normally it's the stainless steels with chromium. And it's seen that the reduction of chromium and the alloying of chromium in the steels happens in two places. One is the ferroalloy production plant, and another one is in the steel making plant. And in this process, there's some energy loss due to the cooling and the remelting of the ferrochrome. To save the energy, and in 1995, Otto Kuhm has introduced a new process. In this process, they have directly used the ferrochrome melt produced in-house and charge this melt directly into the arc furnace to produce stainless steels. Due to the process integration, there's a very high energy saving potential. But still, if we look into the two processes, and we notice that the ferrochrome is just an intermediate for the production of the steels. And therefore, there's still potential if the ferrochrome production processes can be avoided, or at least partially avoided. And to do this, there's another process called the direct alloying by smelting reduction of the chromite ore is proposed. In this process, the chromite ore is charged directly into the pig iron melt, together with the coal and the oxygen injection. During this process, the chromite ore is directly reduced by the carbon in the melt, and then the chromium is directly dissolved in the melt. In another word, the steel is directly alloyed with the chromium. And due to the cutoff of the ferrochrome production process, there's a very high potential for energy saving for this process. But the drawback for this process is the usage of high carbon containing pig iron melt, because the high carbon content in the melt is a prerequisite for the reduction of the chromite ore. And this will inevitably will be a burden for the downstream decarbonization process. Here, we proposed a new process. And we are thinking about to use the solid state reduction process to directly alloy steels with the chromium. And the method is we will mix the chromite ore together with the kind of iron oxide, for example, mill steel, which is from the hot metal working process, and also magnetite, a kind of raw material that has been used for pellets or some other production. The principle is that like this. during the reduction, the iron oxide will be reduced first, and the reduced iron will enhance the carbothermic reduction of chromite due to the decrease of the chromium activity in the formed alloy. And for the applications, we proposed two. The first one, we propose to use a kind of briquettes made from chromite ore plus mill scale plus carbon, and charge such kind of briquettes into the furnace, for example, electric arc furnace, to directly alloy steels with the chromium. And secondly, we also propose we can use a kind of mixture which is made from chromite ore plus magnetite plus anthracite to produce chromium pre-alloyed iron powder or direct reduced iron by the solid-state reduction process. And the benefits, first is the energy saving, because we will avoid the usage of the ferrochrome. And the second is the raw material saving, because we will also expect very high chromium yield from the chromite ore. Here, then I will show some work that I have carried out to show how it can be realized. First, I investigated the carbothermic reduction of synthetic chromite in the presence of the iron powder. The purpose is to investigate how the iron addition can influence the reduction of chromite ore. And it's very aware that in the real industrial process, it's impossible to use the expensive iron powder. So we have proposed to use the mill scale, a kind of byproduct from the hot metal working process, to replace the iron powder. And in this study, I investigated the effect of mill scale on the carbothermic reduction of the chromite ore. It's found that to check the effect of mill scale addition on the reduction of the chromite. And further on, I also investigated the carbothermic reduction of chromite ore together with magnetite to explore the possibility to use such a kind of mix to directly produce it's called chromium pre-alloyed iron powder or direct reduced iron. And in another group of the experiments, I also I also carried out some induction furnace experiments to check the possibility to directly alloy steels with chromium in, for example, in the induction furnace. And the experiments were slightly upscaled from 200 grams to 7 kilos and up to 80 kilos. Then I will show some results. This figure shows the effect of iron powder addition on the carbothermic reduction of the chromite, synthetic chromite. It's seen that the more iron powder is added to the mixture, then the easier the reduction of this synthetic chromite. And similarly, this figure shows the effect of mill scale addition on the carbothermic reduction of the chromite ore, and it shows the same trends. The more mill scale is added to the chromite ore, the easier reduction of the chromite ore in this case. And finally, I can conclude that the mill scale addition or the iron powder addition can significantly enhance the carbothermic reduction of the chromite. And this figure shows the XRD diffractions for the selected phases for the products. And it indicates, we can see that during the reduction, the diffraction peak slightly shifted to the from the right side to the lower to the left side. This indicates the dissolution of the chromium into the into the iron and also the mixed carbides during the reduction process. And this indicates that during the reduction, the chromium was directly dissolved in the added iron. In another word, we can say that the iron was directly alloyed with the chromium by the chromite ore. And in another study, I investigated the carbothermic reduction of chromite together with magnetite. I have designed several different recipes and several different samples. And in different samples, I have different mass ratios of chromite ore to magnetite. And this means that it will generate samples with different mass ratios of chromium to chromium plus iron. And the results show that the more magnetite is added to the sample, and the easier of the reduction of the chromite ore. And by combining the results from the XRD analysis, I can tell that the chromite ore can be almost completely reduced at a temperature below 1473 Kelvin. And this is a critical temperature for the iron powder production. And these two figures shows the same observation of the products, and it's seen that the products are in the powder form, and it's also seen that the chromium was directly dissolved in the formed iron powder. And in the induction furnace experiments, I have made several different recipes of briquettes, and the briquettes was made from chromite ore plus mill scale plus petroleum coke. And I have varied the mass ratio of the chromite to mill scale in the briquettes, and this means that the mass ratio of chromium to chromium plus iron in the briquettes are different. And then in the trials, I charged the briquettes together with the iron scrap into the induction furnace. And during the heating, the briquettes, the oxides in the briquettes were reduced, and of course the chromite ore was reduced. And during the reduction, the chromium directly dissolved in the formed iron. This means that the steels were directly alloyed with chromium. And this figure shows the effect of mill scale addition on the chromium yield from the chromite ore. The more mill scale is added to the briquettes, and the lower mass ratio of chromium to chromium plus iron mass ratio will be, and this will lead to a higher chromium yield. And this is inconsistent to the small scale experiments. And I can tell that the mill scale addition can improve the chromium yield from the chromite ore. Finally, I can draw some conclusions. First, the iron powder mill scale or magnetite can enhance the carbothermic reduction of the chromite, and the yield of chromite from the chromite ore was influenced by the added amounts of the iron powder mill scale or magnetite, whatever. And I also developed two recipes for different applications. The first one is first recipe is the materials made from chromite ore plus mill scale plus carbon, and this kind of mixture can be charged directly into the arc furnace to directly alloy steels with chromium. And secondly, I also propose that the mixture made from chromite ore plus magnetite plus carbonation plus anthracite, for example, can be potentially used to produce chromium pre-alloyed iron powder or direct reduced iron. And the produced iron powder can be used in the powder metallurgy process. And the chromium pre-alloyed direct reduced iron can be used as a charge for the special steel production. And the benefits includes two aspects. The first is the improved energy efficiency, because there's no production of because the production of the ferrochrome can be avoided or partially avoided at least. And secondly, there's a potential to improve the raw materials efficiency, because we can expect very high chromium yield from the raw material chromite ore. And finally, I would like to thank my supervisors, Professor Bo Buchman, Professor Lina Sundquist, and Dr. Qixing Yang for their supervision of this work. And I would also like to thank Sverre Meffers, Hugo Carlson's Foundation, and the Center of Advanced Mining and Metallurgy at Lulu University of Technology for the financial support of this work. And in the end, I also would like to thank the Odin Home for support in this work. Thank you.